All right, hello and welcome back. In this video, we're going to be talking about tree diagrams, which is the second part of simple probability. We started with Venn diagrams in the last video, and this content will kind of build on top of that. I would suggest going and watching that video first, and not required, but it'll help as we go through this content. Before we jump into the topic, there's a few things to go over first. First off, we have a handout for this video, just like the last one. So all the content that we see in this video is all summarized very nicely in a 2-page PDF, and you can find a link to that down in the description. And I will put a copy of what that looks like up on the screen here in a second. So these are 2 pages of the handout, and you can see that they summarize all the intersections, all the unions, and even Bayes' theorem, which we won't get into today, but if you can do conditional probability, then Bayes' theorem is pretty easy as well. So there's the handout. Second thing is that our notes for this video are going to be available down below as well. So notes are in the description, and we're still trying to kind of work out the format for these videos. I think we're mostly going to be emphasizing the key concepts. So format is to emphasize the key visual intuitions here. So we're not trying to learn this topic perfectly. We're really just trying to make sure that we have a good intuitive understanding so that it sticks in our long-term memory a little bit longer, and we get a pretty good grasp of how to solve problems as well. And then lastly, and we always want to mention this, if you are a faster learner, you can watch this in 2 times speed or 1.5 speed. These videos are a little bit slower because we're basically building the notes together as we go through the content, which I kind of like doing instead of having it all kind of pre-formatted beforehand. Okay, so tree diagrams, where should we start? Well, if you remember from Venn diagrams, which we took a look at in the last video, what we want to start off by saying is that for tree diagrams, there's kind of a lot of variations of what a tree diagram can look like. And so what we want to start off by saying is, well, what format should we be familiar with? And we have kind of 2 cases that we can think about. The very first case for tree diagrams is when we have a tree diagram that branches off twice. So this is kind of like our, I guess you could say, standard tree diagram. And our standard tree diagram looks something like this on the left. So a standard tree diagram will have one event, and that event will either happen or not happen. And then after that first event happens, it branches off to our second event. And in our second event, we say that either that event happens or it doesn't happen. And so in total, we get 4 total branches. This type of tree diagram here is going to account for most of the problems that we solve, almost like, I don't know, 75% of them. And then we're going to see some variations, kind of like we see over here. And once again, everything that we learned for this case, so everything from the simple case or the standard case can be extended. So we're going to spend this whole lesson just focusing on the standard case. We'll get to see all the topics that we need to do, and then when we get into advanced questions, which we won't do in this video, but if you see advanced questions and problems, you can just take that knowledge and kind of extend it, just to keep the video, maybe hopefully under 90 minutes. Okay, so one of the things we started with in the last video is we started with our sample space. And so what we can kind of see up there in our standard case is that our sample space is everything that's able to occur. So for a tree diagram, it kind of looks something like this. Let me copy this in. So our standard case that we mentioned up above looks something like this. And our sample space for it is then just these 4 paths. 1, 2, 3, 4. We have 4 possible outcomes. And this is our sample space, U. One of the things we'll see as we work through this is that a great rule of thumb for tree diagrams is that we want to multiply along our branches and add down at the ends of the branches. So like we saw before, for a sample space, the sample space always has to be a total of 100%. It has to add up to 1. And that's also true here. So we can say that once we get our probability, our numbers here, and we add it up, we add up all these outcomes, we should get a total sum of 1 at the end. So that's something to keep in mind. And because these branches here and here, we'll get into it a little bit more later on, is the outcomes of B and B naught and A naught. These branches here also have to sum to 1. But we're getting maybe a little bit ahead of ourselves. So that's our sample space for a tree diagram. Just like before, we're going to say that our probability of A is the probability of event A occurring. And the probability of B, or P of B, is the probability of event B occurring. Just like before, we're going to have our complement probability. And our complement probability is if an event happens, then what's the probability of it not happening? So once again, we can say that the probability of A naught, so we can say this is not A or A naught, is going to be 1 minus the probability of A happening. And then that's also true for B as well. And we saw before that when we have a probability of B and then the complement probability, that those two things have to add up to 1, and they kind of are complementary on our diagram. And that's also true for the tree diagram as well. And so what we can say is that, let's grab our diagram from up here. Our very first branch is our very first event. So either you take the top branch and A happens, or you take the bottom branch and A does not happen. Like we said before, these two branches, A and A naught, must sum to 1. So the really nice thing about tree diagrams is that we can always kind of do a quick sanity check to make sure our numbers make sense, because each of these individual branches always have to sum up to 1. And that's true for every level of our tree diagram. So we also see that for B as well. So we're looking here at the second set of branches, these branches here, and also these branches here, those also have to sum to 1. Now we'll see a little bit later, this is not actually B and B not, but for now we'll just say that it is. We'll say the probability of B plus the probability of B not must also add up to 1. So again, once we have our entire tree diagram filled out, we'll see that it's very easy to verify our numbers, because if they don't add to 1, there's definitely a mistake somewhere in our math. So let's go ahead and highlight that as well as to 1. And we'll see again, this is not exactly B and B not, but for now, it helps us kind of see that. These two are actually a little bit different. All right, the next thing we want to look at is intersection. And this, of course, will be a little bit easier if we're again seeing it for the second time. If you've watched the Venn diagram video, intersection is our and statement. So we can say that the two things that we're talking about, or three things, we can take this up to as many events as we want. The two events have to happen together. So A and B happen together. That's our English statement. Or we could say both happen. That might be better. And our intersection symbol is our upside down U once again. Looks something like that. And so, of course, the very first thing we want to look at is, well, where does intersection happen in our tree diagram? And what we can say is that if we have our standard tree diagram, let's get a copy of that on the screen. What we can say is that A and B occur in this tree diagram when we take our A happens path So A occurs, and then we take the B occurs path as well. So whatever our probabilities are here, maybe it's 1/2 and 1/4, the result that we get here, 1/2 times 1/4, again, multiplying along the branches to give us 1/8. This is our probability of A intersection B. And like we saw before, there's 4 separate cases where we have our complement probability and our intersection, they come together. So we can then say, well, what does probability of A intersection B not look like? Where in our diagram does A happen but B doesn't happen together? So we kind of follow the tree diagram through. We say, well, this one is B naught. Again, it's not actually B naught. We'll get to that in a second. And so we say, well, A happened and then B not happened. So following that path, we can see that the end of that path is the intersection for that. So this path, maybe this has a probability of 3/4. So we say 1/2 times 3/4 gives us 3/8. And we say this is the probability of A intersection B naught. And so following the rules of our tree diagram in the sample space, if we have A naught here, the probability would have to be 1 minus this one, so also 1/2. And then over here, the probability of B, we'll say that it's different, and we'll see why it can be different. We'll say that this one is 1/2 as well. And B naught here is then has to be 1/2, so that these add up to 1, and these add up to 1, and our top branches add up to 1. So if we're looking for the probability of A naught intersection B, we can very clearly see where that lies. So we say, oh, that's going to be right here, the probability of A naught intersection B, which would be equal to 1/4. And then down here, our very last branch, you probably already have this filled in. This is the probability of A naught intersection B naught. And so that's also 1/4. So tree diagrams are really simple, I think, for intersections. And they make a lot of sense visually compared to Venn diagrams because we're asking the question, where does both of these things happen? And we say, oh, we have to follow the path where both events occur or don't occur. And that gives us all 4 possibilities for the intersection. All right, up next we have our union. Our union is a little bit weird for tree diagrams compared to the Venn diagram. So we kind of have trade-offs, the Venn diagram does some things better, the tree diagram does some things better. Our union, which is represented by the large U, let's put that on the screen. The union is our OR statement. So once again, our English statement that we're trying to keep in mind and we want to keep reviewing is event A and event B are both being considered. Specifically, event A or event B or event A and B occur. So we have 3 total conditions, and we want to look at the probability of all 3 of those conditions being met. Either A happens, B happens, or A and B happen. Once again, we need our tree diagram, a copy of that. And let's put that on the screen. Oh, we don't want that. Let's try that one more time. There we go. So if this is our tree diagram, we have a formula that we learned before, and the formula is the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersection B. And so we can see that union is a little bit awkward because we can clearly see our probability of A, and we would think that our probability of B is right here. But once we get down to conditional probability, we're going to see that this is not actually B. You might have a guess that this is actually B given A. But for now, we're going to say we can't calculate our union simply by adding the probability here and here, and then subtracting away the end of it. That would be a big no. So we definitely don't want to do that. Instead, we have to think logically about what our statement is saying. And what our statement is saying is, where does event A happen? So if we start with event A, where in this diagram does event A happen? Well, event A happens in this branch and in this branch, so our top 2 branches. And then if we ask the question, well, where does event B happen? Event B happens in this top branch, in this top branch here, and it also occurs in this 3rd branch here, which we should probably label. So we'll say that this is B, and this is B naught. And then the last thing we want to consider is, where does A and B occur together? And we say, well, that very clearly occurs only in this top branch there. And we can see that if we add all those together, we're kind of again doing a double count. So event A and B together is kind of already included with one of the conditions that we looked at before. Event A and B both include it. So when we're doing this union formula for the tree diagram, instead of thinking in terms of the formula, we're going to instead say, look at all the branches where it occurs and add those branches together. So we know that this is the probability of A intersection B. We know that this one's the probability of A intersection B naught. And then finally, we have the probability of A naught intersection B, like that. And when we add those three together, that gives us our union. This is a formula that we just created right now. You don't have to memorize this. It will not be on your formula sheet. And again, you don't really have to memorize it, because logically we can look at the diagram and see what's happening. So we're saying here that this union in the tree diagram format is actually three intersections all added together. And if you're curious, oops, that should be an intersection. You can go into the Venn diagram and shade these three intersections in, and you should see that when you have these three all added together, they do in fact add up to the union. We can go ahead and put it over here to the side. So if this is A and this is B, and we'll highlight one of these at a time. We'll say, let's do different colors. So let's do yellow. So this yellow one here is going to be A intersection B, that's the middle part. And then we'll do A intersection B naught is going to be this part there. And then our last one, A naught intersection B, is going to be that part. So those three add together does in fact give us the union, everything inside of those two circles. All right, that is our union formula. Again, we don't have to memorize that, but we should know where to find union in our diagram. Next question we're probably asking is, well, we did union in Venn diagrams and there was 4 possibilities. So what about those other 3? What does the probability of A union B naught look like? What's the probability of A naught union B? And lastly, the probability of A naught union B naught. And we can get a quick sketch for those as well. So once again, we're going to need a diagram. One for each of these. Yeah, let's erase before we copy. So starting with our very first one, using the method that we just saw, which of these branches do you think would be included in the probability of A union B naught? Well, we're looking at the case where A occurs. A occurs in this branch, in this branch. We're looking at the place where B does not occur, and B does not occur in this branch and in this branch. And then we're looking for the place where A occurs and B not occurs, which is given by this second branch like that. So we can start to see a pattern that every time we do a union in this standard tree diagram with 2 branches and 2 more branches, that it's always going to have three of the 4 branches highlighted. So you're going to add 3 of the branches together to get your union. All right, repeating that process really quickly for these last two. We're looking for the place in our diagram where A not occurs or A does not occur. So that's going to be down here for these two branches. And then we're looking for the place where B occurs. B occurs in the top branch here and also there. And then finally, where does A not and B occur? That's going to be our last branch, our third branch right there. And doing this one more time for the probability of A naught union B naught. Starting with our first event, A not happening, that's going to be our lower branch. So we say A, let's do pink. A does not happen here and there. Where does B not occur? B not occurs in our second branch and in our last branch. And where does A naught and B naught happen together? That's going to be our final branch, which is here and here. And once again, we see 3 of the 4 branches are included in this union. All right, just labeling these real quick. B naught, B, B naught, A naught, A naught. And so this is all the possibilities for union. Just 4 cases. You can kind of force your way, I guess, through all the possibilities. And then anytime you see these, you know where to go in your diagram. All right. Right after that, we get into conditional probability. Conditional probability is, again, where a condition is given, and then we're looking at the probability within the sample space of that condition. Conditional probability is represented by the vertical bar, and the English for that, I guess we can also put in here, is the probability of an event happening given that another event has occurred. And let's stretch that out. Our conditional probability, once again, is the probability of A given B. That's how it's pronounced. So our second term is the given condition. This gets us into a really interesting kind of space for tree diagrams, in that tree diagrams have always have 2 conditions. So what we've been doing so far, maybe without us even thinking, or maybe you've asked this question already, is that all of our diagrams start with A. And so the question we might ask is, well, what about starting our diagram with B? Could we also do that? And the answer is yes. So every time you do a tree diagram, you really have to decide which event you want to go first and which event you want to go second. As we saw with Venn diagrams, the total number of possibilities for conditional probability is 8. And so we'll kind of see here in a second what that looks like. So this is our first version of the tree diagram. We also have a second version where our event B goes first. So we could have B happening or B not happening. And then after we look at A or A not, A or A not. And what we might notice is that these second set of branches, we've kind of mentioned this already a little bit, is that they're happening after the first event has happened. So we kind of already know some information And what that means is that these, like we mentioned before, is not just an event. This is an event given that another event has already occurred. So this branch up here we call the B branch given that A has occurred, and this is B naught given that A has occurred. And then these down here you could probably guess. This is B given A naught, and B naught given A naught. So in my opinion, tree diagrams really do amazing here because it's very clear to see what a conditional probability means. We're walking down this path and we're saying, well, part of this path has already been traversed, so some condition has already been met. So these are our conditional probabilities. And so oftentimes when a given condition is given in a question, it's much easier to map it out using a tree diagram, as we'll see down below. So this one, following that same type of format, this is A given B, A not given B, A given B not, and A not given B not, like that. We see all four conditional probability cases for, again, the simple tree diagram case. And depending on what question they give you, you'll want to arrange your tree diagram either with the first event and then the second event, or flip the second event and then the first event. You'll see that it'll make it a lot easier to solve out your tree diagram. The great thing about conditional probability here is that in a tree diagram, it makes it a lot easier to see when events are independent, which we're going to talk about next. So actually, let's go ahead and bring that up. So independence we saw with Venn diagrams, and we said we're going to wait until tree diagrams to talk more about this because tree diagrams are a little bit better for helping us understand this topic. Independence. There we go. There was two formulas that we saw for independence, and we kind of just blindly wrote them down and we sort of understood them, but we're going to get a very nice visual intuition of what that means here. So our first formula was the probability of A times the probability of B is equal to the probability of A intersection B, again, only if independent. And we can also say, if this is true, then it does prove that they are independent. This was our test number 1. And then we had the second test as well. We said, well, and this one made a lot more sense. We said the probability of A given B should be equal to the probability of A if they're independent. So if B happened or not, it shouldn't affect the outcome of A happening. And the reverse also had to be true. The probability of B given A had to be equal to the probability of B. If it passed both of these conditions, then we said it passed test number 2. Whoops, there's a typo up there. Test number 1. So if it met both of these conditions down here, it passed test number 2, and it proved that they were independent. Well, if we look up here at these diagrams, we notice that if an event is independent, and maybe it would help to put some numbers in here, we can say maybe this one is 1/4 and 3/4. And we'll say that this one here is 3/8 and 5/8. And this one down here is 4/8 and 4/8. So just 1/2. We can ask the question, is B independent of A? And hopefully we can see very clearly that for this, if A happens, the probability of B happening, it changes. We can see that up in the top branch is 3/8 or 5/8. If A does not happen, the probability of B happening is 1/2 and 1/2. And so we can say very clearly, just by looking at the tree diagram, that this is not true, that they are not independent. And so we can call this the tree diagram sanity check. If we're uncertain whether our test for independence is correct or not once we've worked it out, we can look at our diagram, and these two branches, there and there, must be identical if they're independent. And so what we can say is there's a third test. We can say test number 3. And this one's maybe not as rigorous, but we can say, look at our tree diagram. And if our tree diagram is not showing independence, then we have a pretty good amount of certainty that our result is correct or not. So this is kind of like the tree diagram test for independence. And that's also true, of course, for our other case over here. These two branches must be identical if there is independence. So whether B happens or does not happen, those probabilities should not change or vary. All right, so that's independence. This test here and here is a little bit harder to do with tree diagrams, and this one here I think is not as intuitive, but visually it looks pretty good using the test number 3. Let's see, you know what? There's something we should add to our notes. So if we go up to the very, very top, we talked about the probability of A and the probability of B right here. And we should give ourselves a little note, because something we might be thinking about is, what if our tree diagram is oriented in one way and we want to find the probability of B happening? I'm going to select all of that. Let's do it down here. So maybe we can move just this. Perfect. Okay. So let's say our tree diagram is oriented with A first and B second. We now, of course, know that these are conditional probabilities, but we'll keep it simple. What if we wanted to find the probability of B? What would that look like? Well, what we have to keep in mind is that it's all the branches where B occurs. So if we're trying to find the probability of B, now knowing that these are conditional probabilities, so maybe we should write that in actually. So this is not B, this is B given A, B not given A, B given A not, and B not given A not. Where is B in this diagram if it's not B's? Well, it's every place where B occurs added together. So we have to take the top branch, and we also have to take this middle branch, the third branch, and we have to add those together in order to get our probability of B from this orientation. So depending again on what information they give you in the problem, you want to put B first or A first to make things a little bit more clear. And what we kind of see from here is that we can write down a formula. Again, just we're making this formula up. It's not on the formula sheet. You don't have to memorize this. We're saying the probability of B is equal to this top branch, which hopefully we remember is the probability of A intersection B, and this third branch, which is the probability of A not intersection B. So that's how we find the probability of B when B is not first in the diagram. Okay, moving back down. We looked at union, intersection, conditional probability, independence, and we have one more thing to talk about, and that is mutually exclusive events. And we talked about this of course, again, in the last lesson, and it was very quick and very easy. And it's also true here for tree diagrams as well. This is a very quick topic to discuss. So mutually exclusive events says that A and B cannot occur together. And the math notation translation for that is the intersection, A intersection B, has to be 0. In a Venn diagram, we saw first that we had our two circles, and this circle, well, this circle, like that, and this circle, they were not overlapping at all. And that was a very clear indication that we had two events that were mutually exclusive. It's also true with tree diagrams. We can kind of look at it and spot it right away. So take a second to think about it. What do you think a tree diagram would look like if our intersection, A intersection B, was 0? Well, if we draw out our tree diagram, we have our A event here first, maybe. And then we have our B given A, and our B not given A. And then down below, we have B given A not, and B not given A not. Intersection was one of the first things we did. We said our intersection was this top branch, so this one here. If the events are mutually exclusive, this branch here has to be 0, which means that this branch has to be 1. Again, because these two branches must sum to 1. You can probably think it through. There's other conditions. If they tell us that, well, actually, that's the only case we have to consider. So what we can say is that for Venn diagrams and for tree diagrams, it's very, very easy to see when two events are mutually exclusive. You're going to have a big fat 0 on one of your branches. And in the Venn diagram case, the circles are non-overlapping. All right, that is the last topic for tree diagrams. And so that brings us down to our practice problem, which is the exact same as the practice problem we saw with Venn diagrams. We're just going to rework that question using tree diagrams, just to kind of see, compare and contrast, I guess, how those solutions look different with different diagrams. Some things will be easier, some things will be harder. All right, so our practice problem number 1. Once again, we have two events, A and B, given with these probabilities. They're giving us one conditional probability, and then they're asking us to find a couple of things. Like we mentioned before, they're giving us a conditional probability, and so that means that we probably want to orient our tree diagram in a particular way. What we could say is that our tree diagram, probably best to start this off with our B. And the reason we want to start off with our B is because our top branch up here is the probability of A given B. And we now know that to be 1/2. So again, by orienting our tree diagram in a specific way, that means we can go ahead and fill in probabilities. And the more of this diagram that we can fill in, the easier it will be to solve the rest of this question. So we're going to say a 1/2 here. Probability of B is 1/8. And then again, this is where tree diagrams are a little awkward. We don't have probability of A in here easily. So probability of A, take a second to think about where that would show up. And you remember that the probability of A is all the branches where A occurs. There's two branches where A occurs. We have to add those branches together, and that's going to give us 5/16. So let's go ahead and label these. We get A not given B because, again, This is a tree diagram, all branches sum to 1. We can say that this second branch is also 1/2. And then the probability of B is 1/8. So this one has to be the complement probability, 7/8. And then that leaves us with a branch here, which is A given B naught and A naught given B naught. So we put in all of our numbers. We've used the tree diagram to fill out any other numbers that we can using complement probabilities. And then the last one to consider is our probability of A. So this one here, again, not super obvious where it is, but we have to take this top branch here and also this branch here. Those two will add together to give us 5/16. So what we can say is that this top branch is 1/8 times 1/2. That's 1/16. And then this branch here, we don't know this, so we'll give it a variable x. So we'll give this one the variable x, like that. And so what we can say is that this branch has a probability of 7/8 times x, like that. Well, just like we mentioned, those two branches add up to 5/16. So we can write an equation that says the probability of A is equal to the probability of A intersection B, the top branch, plus the probability of A intersection B naught, which is our third branch, and we just plug those values in. So the probability of A is 5/16. The probability of A intersection B is 1/16. And the probability of A intersection B naught is 7/8 times x. Again, multiplying along the branches. And so here we can move our 1/16 over. We get 4/16 is equal to 7/8 times x. We make our denominator 16 here, so we get 4/16 is equal to 14/16, multiplying the top and bottom by 2. And then to solve for x, we take our 14/16 and we divide it over to the other side. So we can say x is equal to 4/16 divided by 14/16, and using keep change flip, we get 4/16 times 16/14, and that gives us 4/14 after we cancel our top and our bottom. And so we say that this one here is equal to 2/7, like that. So we've solved for x, and keep in mind that x is this probability A given B naught. So this is 2/7. And let's do that in a new color. Let's do blue. Once we have that one unlocked, again, using what we know about tree diagrams, everything sums to 1. We immediately find this one down here as well, and we can see that this is now 5/7, like that. And so going all the way back to the beginning of this discussion on tree diagrams, we can now find the probabilities for each of these branches and see if we did all of our math correctly. So we get 1/8 times 1/2 is 1/16. 1/8 times 1/2 is 1/16. We get 7/8 times 2/7, which now gives us, blue, we get 14/56. And our very last branch Let's do that in blue as well. We get 7 over 8 times 5 over 7. We get 35 over 56. And let's see, 35 plus 14 is 49 over 56. Then we have to get a common denominator. So our final sanity check, basically, to make sure that our tree diagram is valid, is to add all of our probabilities from each branch. And this should equal to 1 if we did all of our math correctly. To avoid doing all that fraction math, we'll just plug it into the calculator real quick. So 1 over 16 plus 1 over 16 is 2 over 16. And then we're adding that to 14 plus 35, so 49 over 56. And I feel like those are not going to add up to 1, but we'll see. So, oh, I guess we could simplify. You know what? We could simplify. So that'd be 1 over 8. And then divide the top by 7 and the bottom by 7. That'd be 7 over 8. And sure enough, we get 1. Okay, we didn't need a calculator actually. All right, so we can see that this is a valid tree diagram. It doesn't guarantee that our math is perfect, but if it fails, then it's a pretty good reminder to go and check to make sure that we did not miss something someplace. Now you might notice we have not answered any of the questions for this problem. We've just taken our time to fill out a complete tree diagram using the information they gave us. And you can do this if you want to. For any problem, you can brute force it, and you can fill out every single number in the diagram, almost always. And once you have your tree diagram complete and full, answering the question can then be a lot faster. Now, I wouldn't recommend doing this. This is actually a little bit slow, but it's a great way to demonstrate how tree diagrams work, how to validate them, and make sure that your math is correct. Okay, so let's take all of that work and move it out of the way and actually get into question A. Question part A is asking us, what's the probability that both events will happen? And so the probability that both events will happen is the probability of A and B happening together, or A intersection B. A intersection B is our top branch. We can see that that is 1 over 16. So pretty quick. Our next one is, what is the probability of only one of the events happening? So what's the probability that only A happens? Well, probability that A happens but B doesn't happen is when A and B does not happen, or A intersection B not. The probability of A intersection B not, we can see very clearly, is given by that third branch which we solved for earlier, and that ended up being 14 over 56, or if we simplify that, we divide the top and bottom by 7, we get 2 over 8, or 1 over 4. Again, very quick, because we did all that pre-work. And then our last one, we're taking a look at part C. It says, what's the probability that neither event will happen? Well, if neither of them happen, that means A doesn't occur and, which is intersection, B does not happen. And that occurs in our bottom branch of our tree diagram. And we can see very clearly that that is going to be 35 over 56. And if we simplify that, dividing by 7 in the top and bottom, we get 5 over 8. And so with that, we have completely solved this problem, and we've also built out a complete tree diagram. Now, if you go back to the Venn diagram video, you could also do the same approach, and you can solve out or fill out your entire Venn diagram and then solve the problems. It's a great approach to take when you're first practicing, just to kind of see how the diagrams work and get comfortable with filling them out. As you get into pacing for exam style questions, of course, you'll want to find the fastest way to solve the question. Just fill in the numbers you need and then get your answer. Okay, so let's do a quick recap of everything we covered in this video, starting from the top. We started off with our set of review sheets. So these are available again, a link down in the description. This is summarizing all the conditional probabilities, where to find them. It shows where to find our unions and our intersections, all 4 cases, and then all 8 cases for the conditional probability. Bayes' theorem we'll get into as well at some point, but Bayes' theorem is just changing the order of the events. So if you're in a tree diagram that's oriented with A first and then B after, you can find your conditional probabilities for those as well. Maybe we should mention that real quick, actually, in a set of notes. Yeah, let's do that real quick. Okay, so we're going to add 1 page to these notes. That will help a lot. Bayes' theorem isn't really great to do with, what's it called? Venn diagrams, but they are really easy to do with tree diagrams. And there's a fancy formula for Bayes' theorem, but we'll see that you can actually use the simple one, and it's visually very easy to understand what's going on. Let's see, I'm going to add a page in. Let's see, is this? Awesome. Okay. So Bayes' theorem. Let's say we have a tree diagram and it's oriented with A first and B second. Again, these are conditional probabilities. And sometimes when we have a tree diagram oriented this way, we might still need to find something like the probability of A given B. And so we say, well, how do we find a conditional probability if it's oriented in this way? You could rebuild your tree diagram in the opposite way and fill in all the numbers and do it. But what we can see is that our formula tells us that this is equal to the probability of A intersection B over the probability of B. And we know how to find both of those things very easily. So starting with the top, if we're looking for the probability of A intersection B, that's our very first path, our top branch. And then if we're looking for the probability of B, we discussed this as well. We said the probability of B is all of the paths or all the branches where B occurs, which is our top branch and our third branch. So all we have to do to calculate this Bayes' theorem, doing conditional probability in the opposite direction of the way that the tree diagram is oriented, is to find our intersection, which is always going to be our single branch, and then our bottom, the probability of B occurring, is always going to be the probability of A intersection B plus the probability of A naught intersection B. This bottom part right here, you'll change it depending on what they're asking for, but if you can visually see what's happening, you highlight your paths and write like this, you can then fill in these formulas and solve. So just to kind of show that that works for a second case, let's take this right here and we'll just copy and paste it. So if they were asking, for instance, well, what about the probability of A not given B not? Could we find that? Well, we sure can. So we're using just our simple conditional probability formula. We're saying the probability of A not given B not is equal to the probability of the intersection of those two things, and then over the probability of the given condition, like that. And so again, we can find those paths in our diagram really quickly. We say, well, A naught intersection B naught is this path right here. Whatever value probability we get here, that's our top, our numerator of our fraction. And then secondly, the probability of B not happening is all the paths where B does not occur. So that's our bottom path, and it's our second path, like that. So whatever those probabilities are there, we simply plug those into the numerator and denominator, and we're good to go. So we're just taking blue. That's not blue. We're taking blue. Whatever our numbers are, again, we're trying to keep it general. And we're dividing by whatever is our green. Our green. And that will give us our final result. Probably A naught given B naught. As you can imagine, we've looked at 2 cases, and then in total, there's going to be 3 total cases. Again, for this kind of standard, 2x2 tree diagram, maybe we can call it that. So these are all the possible formulas and cases you'll need. You're not going to memorize these. This is just, you'll look at the diagram and logically think through, and then those formulas will kind of come to you. All right, all of these notes again will be available down below in the description along with these 2 handouts. And the very first thing that we went through is our, again, 2x2. This is most of what we're going to be doing. Everything else we do, we'll see some of these types of diagrams and other problems. They are just an extension of everything we covered today. Just draw it out, draw out your diagram, and walk through your branches, and it will give you whatever type of answer you're looking for. Our sample space, again, always has to be equal to 1 for 2 diagrams. Every pair of branches, so these branches, and these branches must all sum to 1. And then all of these together must also sum to 1. Our complement probability shows up as the top and bottom branch. And that's true for the second set of branches and the first set of branches. Intersection is when 2 conditions are both met. That's our AND statement. And so our intersections happen at these 4 ends of branches. So there's always 4 intersection possibilities. Really simple, really straightforward for 2 diagrams. For union, a little bit harder to see. Union is always going to be 3 of the 4 branches, as we saw. And so you just kind of go through, highlight them, meeting these conditions, add those branches together, and that gives you your union. And we saw the other 3 cases here. Conditional probability, we get a third test to test for independence. If our second set of branches are identical, then that is telling us that our event is independent of the other event. And we still have our other tests by formula given here and also here. These are not easy to see within a tree diagram because the probability of A is kind of obvious, but our probability of B is like 2 separate branches. So these are not visually that intuitive in a tree diagram. Then mutually exclusive events, really quick and simple. One of your branches are going to be 0 if they are mutually exclusive. And it has to be the branch where A and B both occur. So not the B naught, not the A naught, but A and B together. And then that brought us down into a little extension we just talked about, Bayes' theorem, where sometimes your tree diagram is oriented in one way and you want to find a conditional probability in the other direction. Then you can just kind of highlight your paths, divide, and you're done. Really simple. There's another formula for Bayes' theorem. It's in the formula sheet, and we won't cover it, but if you look at that formula, using the tree diagram, you can see how it works as well. I will leave that. So other Bayes' theorem is in formula sheet. and we will leave it for exploration. And then we get on to our practice problem. We took a slightly different approach for this one. We decided to fill out our entire tree diagram from the get-go, just to practice all the skills that we saw today, looking at complement probabilities, sample space always has to add to 1. Once we had our whole diagram filled out, we solved A, B, and C basically immediately. So it's kind of up to you. The great thing about filling out your whole diagram is you get to validate your tree diagram and all the numbers should add to 1. That doesn't guarantee that your math is correct, but it does give you a little bit of confidence that you're probably not making any small math errors. And that brings us to the end of this practice problem. If there's any errors in this video or questions that you have, put them down below. If you have an interesting idea or theorem you want to share, also make sure to put that in the comment section below. And with that, we are all done, and I will see you in the next one.